Thank you very much. Yeah, so my name is John Britton. I work at GitHub on education. I help people learn how to code and how to use Git. And today I'm going to be talking about the internals of Git, the version control system. Just so I can get a feel for your experience level, can you raise your hand to show if you use Git regularly? OK. If you understand three-stage thinking, what that means in Git. OK, that's good. So I know something I need to talk about. And let's see, if you use GitHub regularly. OK, cool. So now I have an idea of like where we are. So this talk is about Git, the version control system. So as you know, version control is used in software development to kind of keep track of your changes and to more easily collaborate with people on a specific piece of software. I'm going to dive into the kind of under the covers details. I'll have a few slides, but I'm also going to spend a lot of time at the command line. So let's just get started. So this is Git. If you want to use Git, the command line tool, this is what you need to memorize, each one of these commands. No, I'm just joking. There's two sets. There's the porcelain and the plumbing. And Git follows the Unix philosophy of doing one thing well. So each of these commands does exactly one thing, and it does it hopefully pretty well. They're divided into two groups, the porcelain and the plumbing. The porcelain, it's like an analogy from the bathroom. It's the user interface. This is the stuff that you use every day, and it kind of is composed of the stuff down below. So when you do a git pull, what actually happens is it uses a few of the other commands from the plumbing to get the code from the remote server, put it into your working directory, check and see if there are any conflicts, add it to your staging area, and then make a commit. And each one of those phases is actually something that's done from the plumbing. So if I jump, is there anybody who can't read this, not big enough? OK, good. If I jump into my terminal, I can cd into campus party. So I just have a directory here, and there's nothing inside. I can say git init. This is the first command that we're going to talk about. What does it do? It just creates a Git repository. And when you think about a Git repository, what exactly is it? It's just a folder on your normal file system that contains a .git directory. So now that I've done git init, you can see it initialized the empty repository, and that we have a .git directory. Inside of there, this is what it looks like. You can see we have some stuff like, uh-oh, that's no good. There we go. There we go. You have like head, config. You have this objects directory down here, which is really important, and refs. And we'll dig into what those things mean. But if I say git and tab, this is most of the porcelain stuff. So there's a lot there. I'll show you some of them, and we'll dig in. So I asked if you knew what this three-stage thinking was in Git. I'd hope most of you know what the working directory is. So on your machine, when you have a project, you might have like your home directory, projects, the name of your project. In our case, it's my home directory, campus party. That's my working directory. That's the thing that my computer has locally that represents my project right now, this state of my project. My editors can access it. All my tools know how to use it. It's like a standard operating system thing. On the right-hand side, we have the history, all right? And this is the kind of log of changes that you've committed in the past. If you've used Subversion before, you probably are familiar with your working directory and your history, and you commit to your history directly. In Git, we have this third stage in the middle called the staging area. And the way it works is kind of like a shopping cart. You can basically say, here's my working directory. I have a current state of my project. I'm going to change a few files, and I'm going to stage those changes. And what that means is that you're selecting those changes for the next commit. You're getting them ready to be added to the history. So what this means is that you can actually selectively commit things. You can make changes to 10 different files, stage 2 of them, make a commit, and 2 files will be committed to history, but the other 8 will not. So I'll give you a little demonstration of that. So first, I'm going to remove from the .git directory this hooks folder, because we don't need it. Typically, when you're using Git, you're not going to be looking into the .git directory. You should probably stay hands-off. But since this is a Git internals talk, I'm going to be showing you what's inside of the .git directory pretty frequently. So right now, you'll notice that the objects directory is totally empty. it just has these two subfolders, info and pack. I'll start by saying touch readme.md. Any good project starts with a readme. Open it up in my editor, and I'll say, welcome to Campus Party EU. Save it. Uh-oh. I'll do it in this editor. All right, and now if I do ls/lah readme, you can see that my file is 28 bytes. It has something inside of it. The next command we're going to look at is git status. Make this bigger. And git status kind of tells you the state of your repository. Here you can see that we have an initial commit. We haven't made any commits to our repository yet, and we have one file that's untracked. That means it's a file that Git doesn't care about. You've never told Git to do anything with it. And I'm going to open a second window here. cd campus party, ls, cd.git, tree live. So on the right-hand side is a real-time updating view of the .git directory, so what's going on under the hood. And then when I make changes on the left side, you'll see them immediately reflected. So you can see that I have this untracked file, and in my prompt, I also have this kind of cross shape that indicates that I have an untracked file. If you're interested in how that works, I can tell you afterwards, send you some links. Essentially, it's just running git status every time for me. So the next step is, if we look at our slides, if we want to go through this three-stage thinking, we've edited our working directory, we've added a README to it, we've added some content, and now we want to stage that change. We have to get it into the staging area, and then we can commit it to our history so it will be there forever. So to stage it, we use the add command. So I'll say git add README. And when I run that, you'll notice on the right-hand side that it immediately updates. So what happened there? You can see that it has this really weird number-looking thing here. It's a 40-character hex SHA. So it's a hash. I'll show you. Let me see here. Let's do this. So we've added it to the staging area. And since this is just a directory on disk, you might be curious about what's inside of there, right? So if I say cat.git objects a1/2a, whatever, it looks like a bunch of garbage. What it actually is, I just made a command called deflate. I just aliased it in my terminal, which uses zlib to decompress the file. So I can say deflate .git objects a1/2a, whatever. Not using git at all. I'm just using Perl right now. And I can see what's inside. And it shows me blob space 28, welcome to Campus Party EU. And what that means is that this object is a blob, which I'll talk about a little bit more what the different types of objects are. And then 28 is the number of bytes that the file is. And then you have the actual contents of the file. So it's 27 characters and a carriage return, right? So why did Git create this really weird named file, put the contents of it with this extra like starter content, and then compress it? So this right here is a SHA-1 hash. How many people are familiar with what hashes are? Okay. So the key point of hashes is that if you give this algorithm the same input, you'll always get the same output. So this is a way to identify files. In Git, it's actually a way to identify every kind of object. So in our case, there's a command git hash object. This is a plumbing command. You would never really use this on your own. But if we say git hash object and then give it readme, you'll see that it gives us exactly A1 to AB, etc. What it does is it essentially takes the contents of that file, figures out what kind of object it is. It's a blob, figures out the number of bytes, and then it hashes that content. And when I do git add, what happens is it does all that hashing and stuff and puts it into my my repo objects directory and updates the staging area so that when I say git status, I now have a change ready to be committed. So this is this step. We've gone from working to staging. Now we have something that's in staging. Now to demonstrate a little bit about how the staging area works, I can also say git reset, readme, git status, and you'll see untracked file. So now what I've done is I've staged something and I've unstaged it. You'll notice that the file didn't disappear from our objects directory. I'll talk more about how they get taken out of there later, but once it's added, it's just there for a while, and hopefully you'll reference it at some point. So we can re-add, git add readme, git status, and now we have a change ready to be committed. And you'll notice that the right side didn't change at all because it was already in the directory. So if I was to do, for example, cp readme to readme2.md, right, git status, I have one file that's ready to be committed and one that's not. I haven't added the readme2, but if I do git add readme2, you'll notice that nothing changes on the right side because they're the exact same file. The contents of the files are the same, so they're represented by the same object in the git objects directory. Now, they have different file names, but we didn't create a new object, and the reason is that the object that stores files doesn't store the name of the file. It just stores the contents. There are other objects that actually store the file names, and we'll get to them in a little bit. So now I could do, for example, git status, and you can see I have two new files ready to be committed. Git reset readme2, and now I've taken it back out. So we can move things from our working area and stage them so they're ready to be committed, and we'll get to committing next. I'm going to remove readme2 because I don't actually, move readme2 to readme. Status. OK, so now I just have the one that's ready to be committed. But what if I open it up and start editing? Graphs, hashes, compression. So I've edited it. Anybody have an idea of what the staging area or the status command will report? It's actually that this file is in two different states. It's ready to be committed, and it's also not ready to be committed. It's not staged. And what this means is that the version that just had that first line is in the staging area. That's represented by this hash. And the version that I've got currently would be represented by a different hash and is not staged. So I can git add readme, and the new object will show up on the right-hand side. And now git status reports that I have one new file that's ready to be committed. So I've kind of created a file, made some changes to it, gotten it ready to be committed, edited it some more, put the new changes in, and you can see now I have two objects in my objects directory. And that's because Git stores entire files. It doesn't store differences. It stores entire copies of everything when you commit them. So let's move to the next step, which is git commit. When you use git commit, you specify a message. So I'm going to say add a readme. And what this does is it actually takes your work from the staging area, and it saves it into your history so that you can share it with your colleagues. You can put it up on a remote server. You can push it to somebody who's in the same room as you. It just creates a permanent record in your history. So add readme. And we had two objects, and now we have, let's see, 4 objects. So we just created 2 new objects. What could those possibly be? Let's look here. I want to go to this one. So here. We have 4 types of objects in Git. So far, we've looked at blob. Blob stands for any binary file. So in our case, they're just text, but they could be images, they could be videos, they could be CSS files, HTML, C code, headers, whatever. Actual content is stored in a Git object that's called a blob. The next object that we'll talk about is a tree. A tree just represents a directory in your project. So what actually is a directory? A directory contains a bunch of blobs, which are the files, or it contains a bunch of subtrees. And that's kind of what represents the structure of your project. So if you git clone and then you look and you have the top level of your project, you've got a tree which represents, which includes all the files in the top level of your project and subtrees. The next object is a commit, which is what we just created. When we ran git commit, we created an object which is a commit. That gets saved in our history. And then we have tags, which we're not going to talk about tags too much, but they work almost identically to commits, except for they're named. You can say, I want to check out this particular tag by name instead of by hash. So this is what a commit looks like. And we'll start at the bottom. So we created the readme.md file, and we put some text inside of it. And that's where the red is here. We then computed a hash for it when we did git add. And then we created a tree object. And the tree object has entries that specify blob 51D22. That's the hash of the README, and its file name. And then the tree itself has a hash. And then in this case, there's a subtree. We don't have a subtree right now, so we're just the left three objects. Our project. Let's see this. Our project looks something like this area, right? We have these three objects. We have the README. We have a tree that contains the README, and then we have a commit. So the tree again points to some objects. And then the tree has a hash. The commit points to the top level tree. So when you make a commit, every commit in your Git repository points to a tree object. So that means that commits in your history point to a state of your project at a given time. So you have this is what the top level tree of my project looked like when I made this commit. This is what the top level tree of my project looked like when I made the previous commit, and so on and so on. Every time you make a commit, it points to a tree. And then the commit has a bunch of information like the message, who made the commit, who actually committed it, so who wrote the code and who committed it are two different people. And then it has its own hash. So that's what one commit looks like, and I'll show you a little bit more detail. So when I ran git commit, where's my thing? OK, when I ran git commit, it output root commit, which means it's the first commit in my repository, and this hash. F7AE4A8, whatever. And that's right here. And if we say, for example, cat.git objects F7 something, we'll get a bunch of gibberish because it's zlib compressed. So if we say deflate.git objects F7 whatever, we have the same kind of format. So it starts right here. So it says it's a commit object. It's 189 bytes, and it contains the following content. Tree, this, right? With an author, committer, and some more information, and then the message. So that's what a commit object looks like. And Git has a plumbing command called git show, which you can give it, F7AE4, and it will show you a pretty version of this on the terminal. So it says, here's the commit hash, here's the author who made it, the date, and a diff of what was changed. John added these 5 lines to the file. There's also git show -- pretty, which allows you to specify the format that it outputs. And there's a special format called raw, which lets us get more information. So F7AE4. And you can now see the pointer to the tree as well. So I'll just copy that hash, and we'll do the same thing again. We'll do cat.git objects C4 / that. It's gibberish, so I'll deflate that. And you can see here it is. It's a tree object. It's 37 bytes. And then 100644 is actually Unix file modes. So it's a standard object. That 100 is about what kind of object it is. 644 are the Unix permissions. Then you have the file name. And then I'm not exactly sure why it's giving me all this gibberish at the end. It's probably something important. Git ls tree is the kind of plumbing command for working with tree objects, and I'll give it the hash, and it will give me a cleaner output. So it's the same 10644, but it's not telling me how many bytes it is. It's a blob. It points to this hash, and the file name is here. So you can see that, like we said, the tree has the name of the file, the hash, and the type of object. And what's interesting is that the tree, for example, has a hash. How is that hash computed? The hash is based off of the contents of the tree. So when we said, cat that, or that, if we ran SHA-1 hash on this contents, it would end up being A or C4 or whatever it is here. So every object is based off of its contents, and what that means is we have this really nice trickle effect where it's essentially, let's see if we have it. It's essentially, if we have a blob all the way at the bottom, whatever the contents of this blob are going to affect this hash. Whatever this hash equals will be listed here, so it will affect the contents of this tree, which will affect the contents, the value of this hash. That hash will be listed in the next tree, which will then mean this hash is now different because the hash is different, and it goes all the way up to the commit hash. So every single bit of your kind of commit object all the way down to the blobs impacts this in a deterministic way. So for example, if I have a machine and you have a machine, and we both do exactly the same work, I create the exact same file with the same number of bytes, we'll end up creating the same blob. It'll have the same hash. It'll be the same thing in our .git objects directory. Then maybe we create exactly the same tree, exactly the same parent tree, and so on. We'll end up with all the same hashes. But then when we get to the commit object and we both commit at the same time, we'll have different commit hashes because the content of the commit will be different. We'll have different timestamps. We'll have different authors. We'll have different committers. We'll have maybe different messages. But all of the stuff down below will be exactly the same. So when I go and connect to your machine and push my changes to you, I'll transfer my commit, which is just the top-level object, but I won't transfer any of the files because you have all of those files. They're all identified by hashes, and we know you have exactly those files because those hashes match. The reason Git works like this is because the goal of Git as a version control system was to be distributed. So if you take something like Subversion, let me see if I can show this. If you take something like Subversion, it looks something like this. You have V1 of your project, and it actually has a version number. It's R1. And then when I clone the project, or I check out the project and make a commit, I create V2, right? And I have the number n+1. And then if you go and you check out the project and make a commit, you'll make V3. And between the changes, we're actually storing the deltas. So when you make a commit, it's actually saying, John added 5 lines to this file, and it stores that data. So when I want to say clone V3, what Subversion has to do is it has to go to V1 and then apply the deltas from V2, apply the deltas from V3, apply the deltas, so on, so on, and so on. And you end up with that current version. Whereas with Git, you're actually you're doing something like this, where we don't call them V1, we call them by hashes. And when you add 3 files and you change one, what happens is you make a new commit, you add a new file to the objects directory, and then this commit will point to A here and C here. It will go back in time. So you can see as you make commits, you're actually referencing the same objects. So another example would be, say I have 1,000 files in the top level of my project, and I change one of them and make a new commit. We're going to store a new copy of that one file, and the commit will reference the old ones, all the old objects that were there before. So now that we have an idea about the structure of of these commits, the trees and the blobs, we'll take a look at kind of how they're connected to each other. So right now we have a project that's pretty boring. We have a README. It's one commit. We have no history. So let's do some work. So for example, maybe this is a Ruby project. So I'll say nano Ruby or main.rb. I'll say class foo, def some method, puts hello, mean, it doesn't really matter. And class. So I did that. Git status. Git add main.rb, and when we do git add, we're getting ready to commit this this one file. One new object will be created in our objects directory. So now we have 5 objects. And then when we do git commit -m add main.rb, we'll get 2 more objects. What will those 2 objects be? There'll be a new tree, because we need a tree that points to 2 files now. We need a tree that points to the README, which is the pre-existing README, and we need it to point to this new main.rb. We've already got the blob in there for main.rb when we did git add, and we need a commit that points to our tree that has our message. It has the current timestamp, all that information. So that, and so we can say is git show -- pretty equals raw 15b3 5. I'm just grabbing that from here. My computer needs to back up. All right, and I can find the tree, and I can say git ls tree, just to prove that this is actually what's happening, right? So you can see that my tree has 2 objects in it, Unix permissions. They're both blobs. One's readme.md and one's main.rb. This readme is exactly the same hash that it's been all along, so we're not duplicating files as we make commits. Now, if I do git show -- pretty equals raw on head is just shorthand for the latest commit on the branch you have currently checked out. So this is my commit that I just made. You'll see it has one new field called parent. What it does is it points to the parent commit. Which commit came before this? So at this point, the data structure that we have in our repository representing our history is a linked list. We have the latest commit called 15 whatever, 153b35, etc., and it points to a parent commit, which is the one that came before. And if I show git log, which is what it does is it looks at my current commit that I have right now in my working directory, and it shows me all of the history. It will show that I currently have 2 commits, and there's the parent. This is calculated on the fly. When you run git log, it traverses this linked list from where you are, going back into history until it hits the root commit that we saw when we created the first commit. So let's pretend I'm going to do some real work. I'll put this back so you can see the right side. Git scripts, generate random commits, or changes. Ruby 4 Ruby RB. So I just have a script that goes and creates random files, puts random text into them, and commits them one by one. So my git log now shows, make this bigger, shows a substantial history. So we have our README that we added, then our main file, and then a bunch of random work, 4 commits, just so that we have like a little bit more to work with. So now our objects directory is getting to be pretty messy, and it's kind of served its purpose. So I'm going to get rid of it, and I'm now going to show you this other thing called git scripts, git graph live. So what this is I'll put it on the bottom now, because it will be easier to see. So this is a live updating history. So you can see our first commit, first commit that we made, our second commit, and then our random commits that were made automatically. And then we have these yellow things that I'll explain in a second. And as we make commits, so if I say, nano ruby1.rb, and I say another line, I say git add ruby1, git commit -m, add another line. You can see that it immediately updated down below, and these yellow things moved. What are those yellow things? I said that head represents the latest commit that you've currently got checked out. But what does it mean to be checked out? You're throwing around all these terms I don't know. So if we have all of these, let's make one more terminal. Tree live. So now, this is similar to how I was showing you in the .git directory. This is a live view of what's in my current working directory. So in the three-stage thinking, we said we have our working directory, staging area, and history. What we're going to do is we're going to move through history, and we're going to see the working directory update. So if I say git checkout, what it means is make my working directory look like my project did at some point in history. So I can say, go down here and grab this commit, and say, make my working directory look like it did after I made a random change to Ruby 2. So I do that, and you'll notice that I have main, readme, Ruby 1, and Ruby 2. So the other files are gone. Git is now changing my working directory for me when I make a checkout. You'll also notice that head moved. Head is now pointing to this other thing, this older commit a few ago. I can do something like this. I can say git checkout head ~1. Now this is, in Subversion you have revision numbers, you have, first version of code, second version of code, third version of code, and that's really handy because you know kind of how they relate with each other. But these hashes are not ordered, and they're 40 characters long and really hard to understand. So we have this graph navigation, which is just done with, you can say, something. So head is what I'm currently have checked out. ~1 means go back 1. So when I do git checkout head ~1, my working directory updates. I don't have that change anymore. You saw head move down, and that's kind of a way to get around using these hashes to check things out. So what this means is I can say git checkout my current hash caret. Caret means go back 1, so it's even a shorter hand for ~1. You could say ~5, right? In this case, I'll just say caret, and again, it will go back 1. I can say git checkout master, and head will move back up to master, and you'll see all my files come back. So this is where Git gets really powerful. You can essentially have this linked list of history. My project looked like this, then it looked like this, then it looked like this, and you can jump around within it. But what happens if I say go back, git checkout master ~3? So what is master? Well, just from intuition, we can see master points to a thing, just like head did. So we're going to say that it's this one. And we can say go back 3. 1, 2, 3. So it should go to here, 0A, whatever. And it did. All right? And our working directory got updated as we'd expect. So now we have this idea of being able to move around in our history. But what would happen if I said, I don't know, feature nano feature x.rb, and I said some cool new feature is here, right? So now my project, like my working directory, looks like this. I've made a change. You can see that I have an untracked file. Git status shows an untracked file. It also warns me that I'm not on a branch, and I'll talk about that in a minute. But I have an untracked file. What happens if I do git add feature x? Well, it will show up in my objects directory, and my staging area will show that there's something ready to be committed. But what happens if I make a commit from here? If head represents where I currently am in my history, if I make a commit back in history, what will happen? Well, every commit has a pointer to its parent. So what we're going to do is if I say git commit -m work on feature x, you'll see down below that I made a new commit that has a parent that was what head previously was. So this is a branch. This is what people know as branches, right? We didn't specifically create a branch. And the reason I did it this way is that I wanted to show how branching in Git works. Every commit you make is the same as if you made a branch. Because all you're doing when you make a commit is you're making a new object in your history that points to a previous object. So that's all we did is we said, we made a new commit that points to this commit. If we wanted this branch to have a name, we could say something like git branch feature x, and now we'll have a pointer that points to this commit. It just showed up, and now we have feature x. You'll notice that git status, it says not currently on a branch, and my output shows this hash here. That's because I didn't check out the branch by name. I just checked out a commit and made a new commit. If I check out a branch by name, feature x, those warnings will go away. My prompt will be updated. Git status. But my working directory didn't change at all. The only thing that it means to be checked out on a branch is that when you make your next commit, that's what will get updated. So before I was here, and I wasn't on a branch, I was just on head. I just had something checked out with no branch. And then I made a commit, and you saw that head moved because my working directory changed along with the history. If I was on a branch like feature X, and I opened up nano feature X, if I open that up, some more feature work. And since I'm currently on feature X, when I do git add that file, and I do git commit more feature work, what happens is feature X moves. You can see this pointer in my log output down below went forward. So in Git, it means when you say you're on a branch, that means you currently have something selected to move forward when you make your next change. So people get really worried about branching. They think it's really difficult. I just want to show you that branching is nothing special at all. And even to illustrate the point further, I'll show you in here, tree.git. You can see we have this refs directory. Refs heads master and refs heads feature X. Those happen to correspond perfectly with our 2 branches that we have now. So we did before git branch feature X. And what did that do? That created a new branch where we currently are. Right? It's whatever you have in your working directory right now will now be named some branch. But I could say git branch and give it a hash, and it will create a branch that points there. If it updates. Uh-oh. I have to give it a different name. There you go. So it will create a branch at some point in my history. I can do git branch -d feature Y and delete the branch, and it's gone, but I didn't lose any history. And this is important. This is important because branches just are cat.git refs heads feature X. What do you think's inside of here? It's just a hash. Branches are just pointers to hashes that are commits. So commits are branches. Every time you make a commit, you're making a branch. It's no different. So you really shouldn't be afraid of doing it at all. So just to prove the point even further, I'll say, I'll grab git rev parse. So this is another plumbing command. What it does is it takes some kind of like ref path, like head ~1. So what that says is I want to go 1 commit back from where I am, and rev parse will just give me the full hash of that thing. So instead of 09 whatever, I got the full hash. So I'll just grab that and say nano.git refs heads manual branch, paste that in there, close it, and then there's a branch that shows up. So this is like not anything special. It's just a text file that contains the hash of the branch. And I can still use git branch -d manual branch, and it's gone. So let's jump over here for a second. So let's see. We kind of did something like this. We had a version 1 which had a hash. We had a version 2 which had a hash, and they're not versions, right? They just have hashes that identify them. But we can call them 1, 2, 3 if we want. In Subversion, you actually get sequential numbers, and the reason you can do that is because you have a centralized server. Every time you commit, you talk to this central server and you say, what's the current revision? I want to make my revision n+1. Since Git is distributed, you and I can each have a clone of the same repository, do work, make commits. They'll have unique identifiers. They're not n+1 or n+2. We don't have to do any negotiation of what the next version is because they're all based on hashes. That also means that your commit and my commit looks something like this. I made a commit that has a parent, and you made a commit that has that same commit as a parent. So we've essentially made a branch. And if you send me your commit, I'll have something that looks like what we have here. And if I send you mine, you'll have the same. So you can see this is how commits look one by one. But then when we start talking about branches, it looks something like this. So we've gone from a linked list that shows, you have the latest commit, it points to its parent, to what's called a directed acyclic graph. So essentially, you can have any number of commits pointing to any number of parents, as long as there's no loop in the graph, and there's no way to actually create that kind of situation. So let's look at merging. So we can say, for example, let me go here, tree. So my current working directory has a feature in it, and it has 2 of these steps of my initial app. That's because I'm on this branch over here. If I say git checkout master, now I have all Now I have all of my main app, but I don't have any of feature X. And I want both of those together, right? So I can jump back and forth, right? And you'll see my stuff update. Or I can check out master. And the way you bring all this back together is you do git merge. And in traditional version control systems, this can be a really painful process. But it's actually really easy in Git. You just say git merge and what you want to merge. So it's the same if I was on feature X and I said git merge master, as if I was on master and I said git merge feature X. I can merge something into something else. The end result will be exactly the same. You're going to create a new commit that has 2 parents. One which will be this commit here, and one which will be this other commit. Now, the only difference is what branch that new commit will be on. So if I'm on master and I say git merge feature X, the master branch will move forward. If I say I'm on feature X and I do git merge master, the feature X branch will move forward. So I'm on master. This is typically how you would do something like this. You would say git merge feature X, and it will pop up your editor and say, give you a predetermined commit message. I just save it and close it, and it makes a new commit, which has 2 parents. And we can say git show -- pretty equals raw head, because head is the latest commit that I have currently checked out. And you can see that it has 1 parent, 2 parents. Now, if you look on the right side, you can see I have all of my main app, I have my README, and I have my feature. So it's brought everything together. If you look at the graph down below, you can see that my feature X branch is still the same as it was. The branch actually stayed there, which is just a pointer into my history. And my master branch was previously here, this one. It was previously there, but it moved forward to the new merge commit that we created. So you should tidy up after yourself when you do merges. You should say git branch -d feature X. And people sometimes get afraid that they're going get worried they're going to lose their work. But if you watch the bottom, nothing happens except for the pointer disappears, because the master branch now has that commit as a parent. So we have a way to access it. We can start at master and traverse backwards through our history, and we'll get it. If we didn't have, if we had another branch that wasn't merged and we deleted it, so say for example, let's say git branch -d master. Git will, well, I'm on the branch. Git branch foo, git checkout foo, git scripts, generate random changes for foo, foo. So I just did a bunch of stuff on the branch called foo, and if I say git checkout master, git branch -d foo, it will complain to me and say that you have unmerged changes in the foo branch. So Git really looks out for you. It won't let you throw things away that you'll lose. And even if I say git branch -d foo, like capital D, that means just delete it anyways. What happens is it deletes the pointer to the commit that's, it will delete this pointer to this commit. But that commit, I'll just copy it real quick. So I can say here, git branch -d foo. So I just deleted it. And if I look at my history, it's no longer in my history. But if I say git checkout and paste that commit hash that I copied, it's still in my objects directory. And you can see all my work is still there. So it's still available to you, but it will eventually get garbage collected. So I talked about in the beginning when you do git add and something ends up in your objects directory and we're not pointing to it, but it's still going to stay there. It'll stay there for some amount of time, and eventually Git will run a command git gc, probably when you're adding a file or committing. There's like some thresholds. Basically, the things that it throws away have to be more than 90 days old, and there has to be more than like 1,000 objects in your objects directory for it to even run. But it will eventually clean up your mess. So let's see here. Yeah, I think that's it for that. So we've looked at three-stage thinking, the different objects Git stores, the directed acyclic graph, how to navigate around your history. So I can say git checkout master. I can say git checkout head tilde1, which will take me one behind. So this is the previous branch. And in this case, when I said git checkout head tilde1, how did it know which commit to go back to? Since it has two parents, which way does it go? What does it traverse? Git show master show dash pretty equals raw master. It goes to the first parent in the commit, and the first parent in the commit is the one that I was on. So when I said I was on master, and I did git merge feature X, I was on master. So the commit that master was the first parent. So when I go back in history, it's going to traverse that way. So yeah, that's. I think we're getting close to out of time. So I'm going to stop there and take questions.
Thank you, John.
Thank you.
Hi, thank you. I love how you show that nothing magical happens. But my question is, how does this look when you do rebasing, which seems kind of icky?
Sure. I was hoping to show that, but I wanted to get some questions, so I'm glad you asked. So if I do, for example, git scripts, I should really add these to my path. Like 6 foo. So now I was here. It looks kind of messy, but I was on this commit, and then I just made these commits up at the top, on top of it. So I showed you this before, how you can go anywhere in your history and start adding new commits. We've essentially made a branch. What happened was we created a bunch of commits with all of the underlying objects that are supposed to be there. And if I say, for example, git rebase, master, what that will say is the way git rebase works is it takes a look at the changes you've made so far on your branch. It goes back in that history. So I'll look on here. It goes back in the history from head down to where you have a shared ancestor with the thing you're giving it. So I gave it master. So it will go down to this commit, this commit, which is the shared ancestor that head has with master. It will rewind all those commits and put them onto a stack, and then it will go to master, and it will reapply those changes one by one on top of master. But since we know that the commit is like the hashes are like fingerprints, they're every single thing that is part of the commit affects the hash. We're going to get a whole new set of objects that have new hashes. So all of the blobs that represent foo 1, 2, 3, 4, 5, they'll be the same blobs, but we'll end up with new tree objects because they're in the same directory as the README and whatever. And we'll end up with new commit objects because you have new trees and you have all these changes. So even though I'm going to apply the same exact changes, the same work, I'm going to end up with all new hashes for my commits because they're on a different part of the graph. Even the fact that they have a different ancestor will change their commit hash. So if I do git rebase master, you'll now see if we look at our thing here that master is now the ancestor of all of those commits. And our objects directory now looks like I just explained. And to get a little bit fancy, there's this thing called, I'll say git checkout, git reflog. And what this does is it shows you this is like version control for your version control. So rebase is, we said that Git keeps track of your history, but rebase changes your history. So what happens if you screw something up with rebase? Well, you can see that I have a log of all the things that I've done that changed my history. So I can say, here, head at 6 is before I made my rebase. And I can say git reset -- hard head at 6, and I'm going to undo my rebase. So if I update this, of course, since I didn't have a branch there, I have to like figure out what that hash number was and check it out, because it's not going to show up here. Let me just see real quick. It should be this one. Git checkout. That. So there you can see that my rebase is now undone. So that's how it's all kind of under the hood.
Do we have any more questions?
Yeah, I think we have a couple minutes left, but
yeah,
not much.
If I push something, all the trees and changes will get pushed with it.
Yeah, so the way push works is you have a remote. So git remote -v. There's nothing in there. I could say git remote add http github.com/JohnBritton /campus party. And it's not going to check that. I have to give it a name. So git remote -v. Now I have that as my remote. It's just kind of like a bookmark. So I can say git push origin, and that means git push this URL. And it will send all of my repository up to that point. And what it sends is it sends all the objects. So if I, for example, cloned this from GitHub and then made some changes and did a git push, it's only going to send the objects that were changed, the new objects that were added, because objects don't actually change. So we might have added some new trees, new blobs, and new commits, and we'll send those.
I know Git is ridiculously fast, but if I continuously change files that are deep down in the trees, wouldn't that be a possible bottleneck, because it generates a new SHA hash for that and for the trees, all the trees above?
SHA hashing is incredibly fast. It's not like people try and use it for security, and it's like not what it's made for. It's made for hashing super fast. So on a typical machine, you can do tens of thousands, if not hundreds of thousands of hashes in a second. So it's like not even an issue.
No,
in that case,
I meant more in terms of size of the repository.
So I mean, Git does compression across on individual objects. So that's what I showed you. But I didn't show you that if you run. So here, if we do. So here's my objects directory updating live. If I run git gc, which when you have many objects, Git automatically invokes this command. What will happen is it will create these things called pack files. And it's actually compression across objects. So if you have a bunch of objects that all look almost the same, they're going to take up no space. Like they're going to take up next to no space. And it's actually possible for projects that one checkout of the object of the repository could be like 1.5 gigs, and the whole history of everything could be a gig because of compression. So actually, it's not really a problem. Okay. The problem with like file size is when you start having binary assets that are like more than 1 gig or something, and you're changing those repeatedly. Then every time you make a commit, you're creating a new gig of stuff. But Git's not made for binary assets like videos.
Hi, John. Thank you for the talk. I have a question. If I have some changes and I don't want to commit them yet, and I run a git stash, how does it work in this environment?
So let's do that for an example. Touch new file, git status. So let me check out master. So I have a new file that's not done. I haven't done anything with it. Git stash, git status. Nothing happened. This is because this is a file that Git doesn't track. So Git by default doesn't do anything with with non-tracked files. So if you haven't even added it yet, it won't do anything. There's a git help stash. Let me see exactly where it is. Untrack. Yeah, so git stash -u will take untracked files as well. So now there's that. It's not, the changes aren't there anymore. It's taken basically your working directory, anything that's not part of that commit that's currently checked out, it's put it off to the side into a stash area. And what the stash is, it's basically a commit. There's a special set of, I think I can show you tree.git refs stash. So it's basically stored just like a branch. So there's a commit object created. It points to a bunch of stuff. It won't get deleted. It's treated a little bit special because it's the stash. And when I run like git stash list, it has to show them to me. But it works, just like that. It's got a shortcut for it, stash at 0, which is the bottom of the stack, and it has a hash as well. Okay. So git show stash at 0, and there you go. You can see it has a commit hash. So it's as if I committed everything that was currently my working directory. Okay. How are we for time?
Yeah, we are asked to stop.
Okay.
Sorry about this, but thank you all for coming, and thank you very much, John.
So thank you very much. I'm going to go right over to one of these tables. If anybody wants to chat, I've got stickers and stuff, and we can hang out for a while. So thank you.